Welcome to G Fun Facts Online. Today, we are going to strip away the silence of the night sky and look at the violent, roaring reality of how the universe actually works. When we look up, we often see a still painting, stars fixed in place, a quiet, velvet dark. But that is an illusion. The universe is a turbulent ocean of creation, and nowhere is this more terrifyingly beautiful than in the nurseries where stars are born. For decades, astronomers have been trying to peer into these dark clouds, catching only glimpses of the chaos through thick veils of dust. But everything changed with the James Webb Space Telescope. The veil hasn't just been lifted, it has been shredded, and what we are seeing now reveals the supersonic mechanics of stellar birth in detail that is almost impossible to comprehend. Specifically, we are going to talk about a structure that has recently captured the imagination of the entire scientific community. It is an object technically known as Herbig-Haro 49/50, but you might know it better by its new nickname, the cosmic tornado. This isn't just a static sculpture in space. It is a towering, helical pillar of energized gas and dust, a snapshot of a supersonic collision that tells us the story of forces shaping the cosmos on the grandest scales. And the most amazing part is that to understand this cosmic tornado is to understand our own origins. This chaotic tempest is likely a mirror image of the exact environment that spawned our sun and solar system some 4.6 billion years ago. So settle in, because we are going to take a journey 625 light-years away into the dark heart of the constellation Chameleon. To fully appreciate the drama of this object, we have to understand the stage upon which it plays. The cosmic tornado resides deep within a vast complex known as the Chameleon-Weissem molecular cloud. If you were to look at this region with your naked eye, or even a standard backyard telescope, you would see nothing. It looks like a void, a patch of sky devoid of stars. But that emptiness is deceptive. In the infrared eyes of the Webb telescope, this region lights up as a bustling metropolis of stellar activity. These molecular clouds are the coldest, densest parts of the interstellar medium. Think of them as the womb of the galaxy. They are composed primarily of molecular hydrogen and helium, laced with heavier elements and microscopic flecks of carbon and silicates, what we call cosmic dust. These clouds are not calm. They are swirling, turbulent reservoirs where gravity is constantly fighting a war against internal pressure. And when gravity wins, pockets of gas collapse inward. They spin faster and faster as they shrink, until eventually, the nuclear fires of a new star ignite. It is within this darkened theater that the protagonist of our story resides. The star responsible for the cosmic tornado is a Class 1 protostar known as Cedarblad 110 IRS-4. Now, you can't see this star in optical light. It is effectively invisible, shrouded by the very cocoon of material it is feeding from. But even though we can't see the star directly, its presence is announced by its fury. As this infant star feeds, consuming gas from a swirling accretion disk around it, it suffers from a violent form of cosmic indigestion. Powerful magnetic fields, twisted by the rotation of the infalling gas, launch jets of ionized matter from the star's poles. These errant, gentle streams. These jets scream into the surrounding cloud at hundreds of thousands of miles per hour. They act like snowplows, carving out cavities and crashing into the stationary gas ahead of them. The cosmic tornado is the result of one of these massive collisions. Let's break down exactly what we are looking at. The term Herbig-Haro object refers to these specific patches of nebulosity associated with newborn stars. They are transient phenomena. In cosmic time, they last only a blink of an eye, perhaps a few thousand years. But Herbig-Haro 49/50 is unique because of its distinct, vertical, tornado-like appearance. In the high-resolution images captured by Webb's NIR, CAM, and MIRI instruments, the tornado reveals its true nature. It is actually a series of bow shocks. Imagine the waves created by the prow of a ship moving through water. That is what we are seeing here, but on a massive scale. The jet from the protostar doesn't flow smoothly like water from a tap. It burps. It has episodic ejections. Each pulse travels outward, eventually slamming into slower material ejected previously or the surrounding interstellar medium. The texture of this object is fascinating. It looks ropey and twisted. This suggests that the jet is wandering, or precessing. Picture a spinning top on a table. As it rotates, it wobbles. If that top were spewing a stream of paint, the pattern on the walls would be a spiral or a helix. That is exactly what is happening here. The source star is likely wobbling, or perhaps interacting with a binary companion star, causing the jet to trace a corkscrew path through space. As this high-speed material collides with the cloud, it generates shockwaves that heat the gas to thousands of degrees. This superheated gas glows, not in visible light, but in the infrared wavelengths that Webb is designed to detect. The colors in these images are not just for show. They are scientifically mapped to reveal chemical composition. The fiery oranges and reds you might see in the images typically represent molecular hydrogen and carbon monoxide that have been excited by the shocks. These molecules are the cooling agents of the universe. By radiating away the heat generated by the shock, they allow the gas to compress and cool. This is a critical process because it potentially seeds the formation of future stars or planets in the wake of the turbulence. Now, there is a feature in the new image of the cosmic tornado that is particularly striking, something that sits right at the top of the funnel. It looks for all the world like the eye of the storm, or perhaps a companion star being devoured. For years, astronomers observing with less powerful telescopes like Spitzer were puzzled by this. Was it the protostar itself? Was it a massive clump of ejected matter? Well, Webb has solved the mystery, and the answer is a humbling reminder of the sheer scale of space. That bright, fuzzy object perched at the summit is not part of the tornado at all. It is a distant spiral galaxy, located millions of light years in the background. It is a cosmic photobomb. It's a complete coincidence of alignment. The galaxy is seen face-on, with its spiral arms clearly defined, sporting a blue central bulge of older stars and reddish knots of star formation. This chance alignment provides us with an incredible sense of scale. The cosmic tornado, for all its immense size, stretching perhaps a light year in length, is a local event, a microscopic splash in our own galactic backyard. The galaxy in the background is a city of billions of stars, reduced by distance to a mere bauble atop a pillar of dust. Let's dive a bit deeper into the physics here. Why do stars launch these jets in the first place? To understand the cosmic tornado, we have to understand the problem of angular momentum. As a cloud of gas collapses to form a star, it begins to spin. It's the same principle as an ice skater pulling in their arms to spin faster. If this spin were left unchecked, the centrifugal force would eventually tear the young star apart, or at least prevent it from gathering more mass. The star needs a break. It needs a way to shed this excess rotational energy. The jets are that break. The protostar is surrounded by an accretion disk of material falling in. This disk is threaded with magnetic field lines. As the disk spins, these field lines get twisted and wound up like a spring. The tension becomes so great that it snaps, flinging material out along the rotation axis at supersonic speeds. This ejected material carries away the excess angular momentum, allowing the rest of the gas to safely spiral inward and fall onto the star. In the case of Herbig-Haro 49/50, Webb has revealed the complexity of this process. The shocks we see are not uniform. We see knots and clumps where the density of the jet varies. This tells us about the history of the star's feeding habits. A bright knot might correspond to a period where the star gorged itself on a massive clump of dust, causing a violent ejection. A fainter gap might represent a period of relative quiet. In this way, the cosmic tornado is a historical record, a timeline of the star's growth written in glowing gas. It is also important to note that the cosmic tornado does not stand alone. It is part of what astronomers are calling a golden age of protostellar imaging. To really grasp the significance of this object, we should compare it to its siblings, other Herbig-Haro objects recently decoded by Webb, like HH 211 and HH 797. If HH 49/50 is a tornado, then HH 211 is a supersonic lance. Located in the Perseus molecular cloud, HH 211 shows us a textbook bipolar jet, two beams of matter shooting out in opposite directions. Webb revealed that HH 211 is dominated by slow-moving molecular shocks, rich in carbon monoxide and silicon monoxide. This suggests that in the very earliest stages of starbirth, the jets are composed of pristine material plucked directly from the cloud. On the other hand, we have HH 797, which offers a different flavor of chaos. For years, we thought its jet was rotating, but Webb showed us that it's actually two parallel jets flowing side by side. This means the source is a binary pair of stars, where both are launching their own independent jets. It's a tangled mess that looks less like a tornado and more like a cosmic short circuit. Comparing these gives us a view of the diversity of stellar birth. The cosmic tornado lacks the symmetry of the lance-like HH 211, suggesting it is interacting with a much messier environment. Its shape implies a strong precession, perhaps driven by a binary companion on a misaligned orbit, while HH 211 shows us the pristine start of the process, and HH 797 shows us the complexity of binary interaction. The cosmic tornado shows us the turbulence generated when a jet meets the resistance of the molecular cloud. You might be wondering, why are we only seeing this level of detail now? Hubble has imaged Herbig-Haro objects before, and they were spectacular. But Hubble operates primarily in visible light. In these dense, dusty nurseries, visible light is blocked. It scatters off the dust grains, creating dark, opaque walls. Webb operates in the infrared. Infrared light has longer wavelengths that can slip past dust grains without scattering. This allows Webb to look inside the clouds. But it's not just about seeing through the dust, it's about analyzing the chemistry. The instruments used to image the cosmic tornado are tuned to specific colors of infrared light that correspond to specific molecules. For example, when shockwaves hit cold hydrogen gas, they excite the molecules, causing them to emit light at specific wavelengths. Webb's filters isolate this light, allowing astronomers to map the structure of the shockwaves. We also see silicon monoxide, which is a shock tracer. Usually, silicon is locked up in dust grains, but powerful shocks shatter these grains, releasing the silicon into gas. Seeing bright silicon monoxide emission is a smoking gun for violent, high-speed collisions. By combining these chemical layers, astronomers can build a 3D model of the cosmic tornado, measuring the temperature, density, and speed of the gas at every point. Now, let's bring this back home. Why does this matter to you? Because the study of HH 49/50 is essentially a form of archaeology for our own solar system. Our Sun is a middle-aged star, about 4.6 billion years old. Its birth records have long been erased. The gas from which it formed is gone, blown away or incorporated into the planets. The turbulence of its nursery has settled into the clockwork stability of the planets we know today. But once, the Sun was just like Cedar-Blad 110 IRS-4. Once, the solar system was a chaotic nebula, pierced by a bipolar jet. We know this because of the scars left in meteorites. We find calcium-aluminum-rich inclusions in them that show signs of having been flash-heated to extreme temperatures. For decades, the source of this heating was debated. Was it a nearby supernova, a fluctuation in the Sun? Observations of objects like the cosmic tornado suggest that these jets and their associated bow shocks could be the culprits. As the jet slams into the disk or the surrounding cloud, it creates zones of immense heat. Dust grains caught in these tornadoes would be melted and recondensed, forming the minerals we find in meteorites today. Furthermore, the turbulence stirs the pot, mixing elements and isotopes throughout the protoplanetary disk. When we look at the cosmic tornado, we are watching a solar system being baked. We are seeing the mechanism that mixes the ingredients of life: carbon, oxygen, silicon, ensuring that they are distributed to the regions where planets will eventually form. The chaos of the tornado is actually a necessary mixing process, a cosmic blender that ensures the chemical richness of future worlds. This interaction between the jet and the cloud is a double-edged sword. On one hand, the jet is destructive. It blasts away the envelope of gas, limiting the final mass of the star. If the jet is too powerful, it might strip the accretion disk entirely, halting the formation of planets. The cavities carved by the cosmic tornado represent material that will never become part of a star or planet. It is lost to the interstellar medium. On the other hand, this destruction is creative. The shockwaves compress the surrounding gas. If a shockwave hits a dense clump of gas, it might compress it enough to trigger gravitational collapse. In this scenario, the death throes of one star's formation become the birth pangs of another. This is known as triggered star formation. The cosmic tornado, as it whips through the chameleon cloud, may be setting off a chain reaction, igniting a new generation of stars along its path. This feedback loop is crucial for the evolution of galaxies. Without jets and outflows, star formation would be inefficient. The gas would simply sit there. The turbulence injected by things like this keeps the galaxy alive, regulating the rate at which stars form. We are living in an exciting time because the image of the cosmic tornado is just a single frame in a movie that lasts thousands of years. But astronomy is changing. With the precision of JWST, we can hope to see changes on human timescales. By revisiting HH 49/50 in 5 or 10 years, astronomers will be able to measure the movement of the knots. We will see them move against the background stars. We will see the shockwaves expand and fade. This is called time domain astronomy. It will allow us to measure the exact speed of the jet, the deceleration of the shocks, and the cooling rates of the gas. We will stop guessing at the physics and start measuring it directly. Future observations will also focus on the source star itself, using arrays like ALMA in conjunction with Webb to pierce even deeper into the dust, imaging the accretion disk itself. We want to see the launch pad, where the magnetic fields rip the gas from the disk and fling it into the tornado. In conclusion, the cosmic tornado, Herbig-Haro 49/50, is a masterpiece of nature. Visually, it is stunning. A pillar of fire set against the cold velvet of space, crowned by a distant galaxy, but its true beauty lies in what it tells us. It decodes the chaos of our own origins. It reveals the invisible forces of magnetism and turbulence that sculpt the universe. Webb has turned the lights on in the nursery. We are no longer stumbling in the dark, guessing at the shapes of the monsters in the room. We see them clearly now. We see the violence, the energy, and the intricate dance of matter that leads to the quiet miracle of a stable star. The cosmic tornado is a storm, yes. But it is a storm that leaves behind the calm of creation, a chaotic crucible from which worlds, and perhaps life itself, will eventually emerge. In watching it spin, We are watching the universe breathe, exhale, and create. Thanks for listening to G Fun Facts Online, and keep looking up.